Have you ever imagined building a complex structure, not with Legos, but with something, well, far, far smaller? Think about constructing molecules atom by atom, specifically carbon atoms, which, form the literal backbone of nearly all organic molecules. Every protein, every piece of life on Earth.
Foundational.
Exactly. That's the incredible precision we're talking about today in a molecular construction project, far more intricate than any building set, just incredible precision.
Yeah.
Today, we're taking a deep dive into the fascinating world of advanced organic chemistry, specifically Chapter 2 of Advanced Organic Chemistry, Part B Reactions, and Synthesis, 5th ed.
A classic text.
Absolutely. Our mission, to pull out the most vital insights on how chemists meticulously build new carbon-carbon bonds. We're going to try and untangle the fundamental reaction types, the clever strategies for synthesis, and crucially, the ingenious ways they control the outcomes, ensuring they construct exactly what they set out to make.
And when we talk about building carbon-carbon bonds, we're really talking about the foundational steps needed to synthesize, well, virtually any complex molecule you can imagine.
Right. Drugs, materials.
Exactly. Whether it's a life-saving pharmaceutical, an intricate natural product, or even an advanced new material. This chapter and our deep dive today really focuses on two main categories of these bond-forming reactions.
Wow.
First, you've got reactions where carbon nucleophiles interact with carbonyl compounds. Those are often your aldehydes and ketones. And second, the equally vital conjugate additions, which are also widely known as Michael reactions.
The Michael reaction, yeah.
These two types are truly the bedrock for creating molecular complexity. They're the absolute core.
So, how do we even begin this molecular construction? Let's start with our fundamental building blocks, or maybe our molecular players.
Good place to start.
In organic chemistry, you constantly encounter terms like nucleophiles and electrophiles. Let's kick things off with carbon nucleophiles. Imagine a carbon atom that's just brimming with electrons, maybe carrying a negative charge, or perhaps it have a lone pair of electrons just waiting to be shared.
Electron-rich.
Exactly. That's our carbon nucleophile. It's electron-rich, and it's actively seeking out a positive or electron-deficient center. Think of it as a carbon atom looking for a partner, eager to form a new bond.
That's a perfect way to put it. And the source material, this chapter, highlights various forms these carbon nucleophiles can take.
Like what?
Well, we primarily encounter carbanions, where a carbon atom literally bears a negative charge. This charge is often stabilized by nearby electron-withdrawing groups, things like cyanide or maybe sulfonyl groups.
Okay, so it's not just a naked charge?
Not usually, no. Stabilization helps. Then there are halides, which are intriguing molecules where adjacent atoms carry opposite formal charges, like a phosphorus halide or a sulfur halide.
Right, those phosphorus halides in the Wittig reaction.
Precisely. These are the reactive electron-donating attackers in our molecular game, ready to jump in and form that new connection.
Okay, so if we have these eager, electron-rich carbon nucleophiles, they clearly need an electron-deficient partner, right?
They do, something to attack.
And in many of these reactions, that partner is a carbonyl compound. Picture a carbon atom double bonded to an oxygen.
C double bond O, the classic carbonyl.
No, an oxygen is a bit of an electron hog. It's highly electron negative, meaning it pulls electron density away from that carbon.
It hates a dipole.
Exactly. This leaves the carbonyl carbon with a partial positive charge, making it electron deficient and incredibly attractive to those electron-rich nucleophiles we just described. It's the perfect bullseye for a new bond to form.
Exactly. The general reaction is quite elegant and follows a pretty consistent pattern. A carbon nucleophile, it's represented as ZC, where Z might be a stabilizing group or just the negative charge, approaches and attacks that partially positive carbonyl carbon. This direct attack forms a brand new carbon-carbon bond.
Okay.
Meanwhile, the oxygen atom, having accepted the double bond's electrons, gains a negative charge, becoming an alkoxide.
CO-.
Right. This alkoxide is typically then protonated, usually by adding a mild acid in the workup, to yield an alcohol, COH.
Got it.
This is the fundamental addition framework that underpins so many of the complex reactions we'll unravel today.
But the bullseye isn't always a direct carbonyl carbon. Sometimes these nucleophiles find a different weak spot, right? Which leads us to conjugate addition, also widely known as the Michael reaction.
That's right, the Michael reaction. Here, instead of attacking the carbonyl carbon directly, what we call 1-2 addition, the nucleophiles add to electron-deficient double or even triple bonds further down the chain, usually in a 1-bar-4 fashion relative to the activating group.
So it's like finding a different side entrance into the molecule, not the front door.
Exactly. And for this side entrance attack to happen, there's a crucial requirement. The double or triple bond must be activated by an electron withdrawing group, an EWG attached to it.
Ah, okay. It needs that pull.
It does. Think of groups like another carbonyl, or maybe a nitro group, or a cyano group. This EWG is vital because it stabilizes the negative charge that forms on the intermediate after the nucleophile attacks.
Right. It spreads out the charge, makes it more stable.
Precisely. It effectively makes that carbon multiple bond an electrophilic magnet, drawing in the nucleophile. For this deep dive, we'll specifically focus on reactions between enolates, which are a common and very powerful type of carbon nucleophile, and alpha-beta unsaturated carbonyl compounds, or nitroalkenes.
Those are the classic Michael acceptors.
They are. These are classic and incredibly useful examples of conjugate addition.
All right, let's dive into what's often considered a true workhorse of organic synthesis, the aldol reaction.
Yes, the aldol. Absolutely fundamental.
This isn't just some niche chemical curiosity, right? It's a foundational molecular construction tool. The aldol reaction is absolutely vital because it's a remarkably powerful way for chemists to quickly build larger, more intricate molecules from simpler starting materials.
It really is building complexity quickly.
Imagine starting with small molecular Lego bricks and snapping them together to create complex multifunctional units, often adding multiple precise points of 3D arrangement in a single step. That's the aldol. It involves those carbon nucleophiles we talked about, specifically enolates or enols, adding to carbonyl compounds.
Indeed. And the versatility of the generalized aldol reaction is just astounding because nearly all stabilized carbanions can potentially participate.
Really? Almost all?
Well, a very wide range. This includes a wide array of enolates derived from common building blocks like aldehydes, ketones, esters, even amides.
Wow.
Beyond those, carbanions from nitriles and even some phosphorus or sulfur-stabilized carbanions and alkylates can also add to carbonyl groups. This broad scope demonstrates why it's such a fundamental reaction. Our particular focus today, though, will be on how chemists precisely control where the bond forms. That's regiochemistry.
Right.
And how the atoms are oriented in 3D space stereochemistry, especially for reactions involving ketones and aldehydes. That's where the real subtlety lies.
You've hit on something absolutely critical there. When we're synthesizing complex molecules, particularly for things like pharmaceuticals that need to fit perfectly into a biological receptor.
Like a lock and key.
Exactly. Simply forming a bond isn't enough. We need surgical precision. That's where the challenge of controlling regiochemistry, where exactly on the molecule the bond forms, and stereochemistry, the precise 3D arrangement of atoms in space, becomes paramount. It's the difference between a functional key and, well, a useless piece of metal.
Absolutely. It's everything in modern synthesis. To achieve that level of precision, chemists often employ what's known as directed aldol addition.
Directed. Okay.
This is a really smart strategy where the nucleophilic enolate is pre-formed. Instead of just letting it generate spontaneously in the reaction mixture, which could lead to multiple unwanted isomers or side reactions, it's carefully deprotonated in a controlled way, usually with lithium as a counterion in a specific aprotic solvent that doesn't interfere, and critically at very low temperatures like minus 78 Celsius.
Minus 78. Dry ice temperature.
Exactly. This meticulous preformation ensures that one reactant acts exclusively as the nucleophile and the other as the electrophile, greatly minimizing side reactions and maximizing the desired product. It gives you control.
And this leads us to a truly fundamental concept in synthetic chemistry: kinetic versus thermodynamic control.
Yes, a classic dichotomy.
Think of it like two different approaches to cooking a meal, maybe. Under kinetic control, it's all about speed.
Fastest product wins.
Right. You use strong bases, keep the temperature really low, just like you said. This environment favors the kinetic enolate, which is the one that forms the fastest, even if it's not the most stable possible molecular arrangement.
It's the lowest energy barrier to formation.
Okay. The addition step happens so rapidly that it essentially freezes that initial fast-formed product before it has a chance to rearrange or equilibrate. It's like a quick-bake recipe, ensuring a specific, non-equilibrated product.
That's a good analogy. In contrast, thermodynamic control is more like slow cooking.
Letting it simmer.
Exactly. You might use less base, perhaps higher temperatures, or maybe specific protoget or polar solvents. Here, the aldol reaction becomes reversible.
Ah, it can go backwards.
It can. This reversibility allows the system to equilibrate. The product ratio isn't determined by which product forms fastest, but by which combination of products is the most stable overall, the lowest in energy.
So it finds the most stable state eventually.
The system has time to find its lowest energy state, leading to the thermodynamically favored product, which might be a completely different isomer than what you'd get under kinetic control. It's about letting the flavors or the molecular arrangements balance out to find the tastiest and most stable result.
That's a great analogy. So with these principles in mind, let's talk about the specific power players that allow chemists to guide these reactions. The metal enolates.
Right. The Counturian matters a lot.
Lithium enolates, for instance, are a kind of reactive standard, right?
Right. They are. Very common, very useful. They're typically formed under those kinetically controlled conditions we just discussed, using a strong lithium-containing base like LDA, lithium disisopropylamide.
LDA. Okay.
And once formed, they're incredibly reactive. They add rapidly to aldehydes, even at very low temperatures, like that minus 78 degrees. This low temperature is key for ensuring kinetic control and achieving high selectivity, really steering the reaction towards a precise outcome.
So the low temperature locks in the kinetic product.
Primarily, yes. And the secret behind the precise 3D outcome or diastereoselectivity of these lithium enolate aldol reactions often lies in what's called a cyclic transition state.
Cyclic, okay, like a ring.
Exactly. Imagine both the carbonyl oxygen from your aldehyde or ketone and the enolate oxygen coordinating tightly to the lithium chemication. The lithium acts as a Lewis acid, essentially pulling the reactants together in a specific way.
Acting like molecular glue.
Sort of, yeah. It organizes them. This arrangement forces the reaction through a specific, highly ordered intermediate state known as a chair-like transition state, which structurally resembles a cyclohexane chair.
Like a chair conformation.
Precisely. This model is invaluable because it allows us to predict the specific 3D arrangement, the relative stereochemistry of the product.
And here's where it gets really interesting and useful, right? This chair-like transition state has a profound consequence for stereochemistry. The reaction becomes stereospecific with respect to the starting enolate's geometry.
That's the crucial link.
What that means is if you start with an enolate, which refers to a specific arrangement around the double bond.
E for enkegaden, opposite sides.
Right, you consistently produce the anti-aldol product. Think of anti as two groups being on opposite sides relative to each other in the new molecule.
Anti-paraplanar arrangement in the transition state leads to the anti-product.
Conversely, if you use a Z-enolate,
Z for Zusammen, together,
it reliably leads to the syn-aldol product, where those two groups are on the same side, almost like your thumbs when you clasp your hands.
Syn-paraplanar leads to syn-product.
And this isn't just theoretical. It's been elegantly confirmed using special deuterium-labeled enolates, right? Allowing chemists to trace the exact pathway and prove this predictable relationship.
Absolutely. It's well established. E goes to anti, Z goes to syn. It's a cornerstone prediction for lithium enolate aldol reactions via this chair-like transition state.
And does the structure of the enolate itself play a role, like how bulky the groups are?
Oh, definitely. This predictable relationship, especially the preference for syn products from Z-enolates, is also evident when you work with ketone enolates that have bulky substituents.
Oh.
For example, enolates with a bulky T-butyl group show a much stronger preference for forming the syn-aldol than those with smaller isopropyl or ethyl groups.
Why is that?
It directly correlates with how easily the Z-enolate forms initially during the deprotonation step. Bulky groups often favor the formation of the Z-enolate kinetically.
I see. So the bulkiness influences the EZ ratio of the enolate itself.
Exactly. It's a practical design principle for chemists. If you want to push for a specific syn product, sometimes introducing a bulky group on your starting ketone can help you achieve that by favoring the Z-enolate formation.
Clever. But what if you have less substituted ketones? Is controlling the EZ ratio still easy?
That's actually a significant challenge for less substituted ketones. Getting a clean E or Z enolate isn't always straightforward. But chemists have developed methods to modify this ratio.
Like what?
Well, using specific base mixtures like lithium tetramethylpiperidine, LiTMP with lithium bromide, or employing weakly basic lithium anhydrides, or even certain acrylamide bases can influence the EZ outcome. Table 2.1 in the book actually illustrates this quite nicely, showing how the R1 group on the ketone affects the ZE ratio and the subsequent syn.anti-product ratio.
Right, so there are ways to tune it, even in tricky cases.
There are, yes. Requires careful optimization, but it's possible.
So if lithium enolates are our workhorses, you mentioned boron enolates are often considered the precision tools.
It's a fair description, yeah. Boron enolates offer another dimension of control, particularly regarding stereoselectivity. They're typically prepared by reacting a ketone with a dialkyl boron trifluoromethensulfonate, or triflate for short,
Boron triflate, okay.
and a tertiary enamines, like Hooning's base. What's particularly noteworthy is that boron enolates, especially those formed with bulky amines, show a strong preference for forming Z-enolates.
Z-enolates again.
Yes, and as we've established, Z-enolates predictably lead to syn stereoisomers in the aldol products through that chair-like transition state model.
So boron triflates tend to give syn products.
Generally, yes, especially with bulky amines. But here's the clever part. If you use dialkylboron chlorides instead of triflates, you can sometimes favor the formation of E-enolates.
So you can switch selectivity just by changing the boron reagent.
Exactly. Enolates, of course, would then lead predominantly to the anti-aldol product. This ability to switch stereoselectivity just by tweaking the boron reagent is a testament to the subtle interplay of factors like reactant conformation, stereoelectronics, like how the proton needs to be aligned for removal, and the sheer size of the boron ligand.
Incredible control.
It really is. Chemists can essentially dial in the desired stereochemistry much more reliably in many cases compared to just lithium. Table 2.2 in the chapter is packed with data showing these effects.
So beyond lithium and boron, you mentioned other metals, titanium, tin, zirconium.
Right. These metal enolates are also very useful. They sort of lie somewhere in character between the highly ionic lithium enolates and the more covalent boron enolates.
Intermediate character.
Exactly. This allows them to coordinate with additional ligands, leading to more complex, structured intermediates. We see tetra, penta, even hexacoordinate structures.
More coordination options.
Yes, and this leads to a unique feature, the ability to form chelated transition states.
Chelian again, like the metal grabbing multiple points.
Precisely. The metal ion coordinates not just with the enolate oxygen, but also with other nearby donor groups in the electrophile, like an oxygen or nitrogen atom. This chelation brings things together very tightly and can exert powerful stereo control. Sometimes you even form 8 complexes where the metal formally has a negative charge, which can enhance the nucleophilicity.
So how are titanium enolates used, for instance?
Titanium enolates are generated, for example, from ketones using titanium tetrachloride, TTL4, and a tertiary amine. They tend to form Z-enolates, leading to syn stereochemistry, again likely through a cyclic transition state.
Synecan.
They are frequently used in complex molecule synthesis, especially when combined with those chiral auxiliaries we'll talk about later, like N-acylocosylidinones. They offer reliable syn selectivity.
What about tin and zirconium?
Tin enolates, both SASIM and SN-LOMI, are reactive. Tin-2-triflate often leads to syn-selective aldol additions, but interestingly, sometimes via an open, non-cyclic transition state to avoid unfavorable interactions. Triion-butylstanol enolates, when activated, can actually give antiproducts. Zirconium enolates, formed with zirconium tetra-T-butoxide, are mildly basic, and their stereoselectivity also suggests a cyclic transition state, often similar to boron.
So many options, each with its nuances.
It's a rich toolkit. The key factors governing the final 3D shape, the diastereoselectivity, are consistently arise. The enolate configuration, Ionti, Z-asin, the Lewis acid's ability to promote tight coordination, favoring cyclic transition states, the chair-like conformation itself, and the presence of those extra coordination sites for chelation.
And what about ester enolates? We mentioned ketones and aldehydes, but esters are common too.
Right. Ester enolates are also incredibly useful in aldol-type reactions. For simple esters like ethyl propanate reacting with LDA and THF, the E-enolate is generally preferred kinetically.
E-enolate for simple esters.
Yes. But if you want to encourage the formation of Z-enolates from esters, you can add special co-solvents like HMPA or DMPU. These strongly solvate the lithiumation, pulling it away from the enolate and influencing its geometry towards Z.
Manipulating the collocation environment.
Exactly. Boron enolates from esters, and amides often give Z-enolates too, leading to synadducts, although there are exceptions with very bulky groups. And tin-2 enolates, for instance, from cyoesters, also show good syn selectivity, again highlighting the metal ion's influence.
It's really about controlling that initial enolate geometry.
That's a huge part of it, yes.
Okay, let's shift gears slightly to the Mukayama aldol reaction. You mentioned this uses a silly switch. What's that about?
Right, the Mukayama aldol. It's an aldol-type reaction, but instead of using traditional metal enolates formed with strong bases, it employs enolate equivalents, specifically silyenol ethers, which you can make from ketones, or silly-ketone acetols, which come from esters or amides.
So silicon-containing enolate mimics.
Exactly. These aren't very reactive on their own, but they become highly reactive towards aldehydes or ketones when activated by a Lewis acid.
Ah, the Lewis acid is the key.
It is. The mechanism is quite clever.
Yeah.
The Lewis acid, like titanium tetrachloride or boron trifluoride, first activates the carbonyl compound, making it even more receptive to attack, more electrophilic.
Primes the target.
Precisely. Then, as the new carbon-carbon bond forms between the silly-enol ether and the activated carbonyl, the cilia group, that silly silicon, is neatly transferred away from the enolate equivalent onto the newly forming alkoxide oxygen.
So the silicon jumps over.
It does. This transfer is thermodynamically favorable and drives the reaction forward, enabling that crucial carbon-carbon bond formation. Chemists have a robust toolkit of Lewis acids for this, from common ones like BF3, TiCl4, SNCl4, to even more exotic ones like lanthanide, halides, or special zirconium species. It showcases the versatility of this approach.
Are there different ideas about how exactly the Lewis acid works?
Yes, there are multiple proposed catalytic mechanisms. It could be simple Lewis acid activation of the carbonyl, like we just said, or there could be a direct exchange where the Lewis acid swaps with the silyl group on the enolate equivalent first. Or, in some cases, it might activate a catalytic cycle where a trimethylsilication itself becomes the active catalyst.
Interesting complexity.
It is. And these reactions also work well with acetyls, not just aldehydes and ketones, which allows chemists to introduce protected alcohol groups into complex molecules.
What about stereoselectivity in the Mukayama reaction? Is it the same EZ to anti-Weedy rule?
That's an important point. While the overall stereoselectivity issues are similar to traditional aldol reactions, you still worry about syn versus anti-apera. The Mukayama reaction often shows a tendency towards more flexible acyclic transition states rather than the rigid chair-like ones.
Ah, okay. Not necessarily cyclic.
Right. This can sometimes reduce the direct influence of the starting silyl enol ethers E or Z configuration on the final Sinanti stereoselectivity. The connection isn't always as strict as with lithium or boron enolates. It's an important nuance for chemists to consider when planning a synthesis using this method.
Makes sense. It adds another layer of complexity or maybe opportunity, depending on how you look at it.
Definitely.
So when we talk about building complex molecules, particularly those with a specific handedness or chirality, we really enter the realm of molecular origami, don't we?
That's a great way to put it. Mastering stereo control in aldol reactions becomes absolutely paramount, especially if one of our starting materials, like an aldehyde, already has a chiral center, a stereo center.
Right, because that introduces facial selectivity.
Exactly. The problem is that such a chiral aldehyde presents two distinct faces for the incoming nucleophile, the enolate, to attack. It can come from the top face or the bottom face, leading to different stereoisomers.
And if the enolate is also chiral.
Then it gets even more complicated. You could potentially form up to 8 different stereoisomers from a racemic aldehyde, reacting with a racemic enolate. That's a lot of potential products, and a huge challenge for a chemist trying to make just one of them specifically.
It's a massive challenge. How do chemists tackle it? What controls which face gets attacked?
Well, for aldehydes with simple non-polar substituents like alkyl or aryl groups steric effects, basically how much space atoms take up are often the key deciding factor.
It's bumping into each other.
Pretty much. The Falcon-Ann model is a very useful predictor here. It suggests that the largest group on the carbon next to the carbonyl will orient itself anti-180 degrees away to the incoming nucleophile to minimize these steric clashes in the transition state. This predicts a specific approach trajectory and thus a specific 3D product, usually the 3-4-syn product in aldol terms.
So the molecule arranges itself to be least crowded during the reaction.
That's the essence of it for simple steric control. But what happens if there are other groups in the molecule that can interact electronically or with the metal center?
Ah, like those donor groups you mentioned.
Exactly. That's where the powerful concept of chelation control comes in. It can act like an internal compass for the reaction. If there are nearby oxygen atoms or other donor groups within the aldehyde, like at the alpha or beta position, they can coordinate or chelate with the Lewis acid, be it lithium, titanium, tin, zirconium. This forms a tightly bound, rigid, chelated transition state.
Locking it in place.
Precisely. This chelation can actually override those simple steric effects predicted by the Falcon-Ann model. It directs the enolate's attack to a specific face of the molecule because the chelation blocks one side or forces a specific conformation.
Can you give an example?
Sure. Alpha-oxygenated aldehydes reacting with TQ4 often give specific 2,3-syn, 3,4-syn products because the titanium chelates to both the carbonyl oxygen and the alpha oxygen, forcing a specific cyclic transition state. Beta-oxygenated aldehydes under chelation control might give 3005 antiproducts. Figure 2.1 in the text shows a tin complex illustrating this kind of steric shielding due to chelation. It shows just how much influence the metal and the surrounding atoms can have, completely changing the stereochemical outcome compared to non-chelating conditions.
Wow, so chelation can totally flip the expected outcome based on sterics alone.
It absolutely can. It's a very powerful control element. And then you also have polar effects.
Polar effects, what are those?
Sometimes, heteroatom substituents like alkoxy groups introduce strong dipolar interactions. The molecule might adopt a transition state conformation that minimizes the repulsion between the CO bond of the alkoxy group and the CO bond of the carbonyl. This minimization of dipole repulsion can also override simple steric models and lead to different selectivity patterns, especially for Z enolates.
So it's a complex interplay. Sterics, chelation, polar effect.
Exactly. And the choice of Lewis acid is paramount because it determines whether chelation is possible and how strong it might be. Scheme 2.3 in the book gives some really nice concrete examples illustrating these different control mechanisms in action. It's a puzzle, but chemists have developed a good understanding of these pieces.
Okay, so that's facial selectivity of the aldehyde. What about the enolate? Can it have facial selectivity too?
Oh, absolutely. If the enolate itself has a chiral center, its own 3D structure profoundly influences the outcome as well.
How does that work?
Well, if the chiral center on the enolate is non-chelating, the two new stereocenters formed often adopt a specific relationship, often syn, again consistent with the cyclic transition state model, where steric interactions within the enolate part dictate the preferred approach.
But what if there are chelating groups on the enolate? Like oxygen?
Then it gets really interesting and highly dependent on the nature of that oxygenated substituent and the metal. For example, certain silicon-protecting groups like TBDMS on an alpha-oxygenated enolate often lead to high selectivity via a non-chelated transition state. But a benzyloxy group in the same position might be less selective because it can chelate, leading to competing pathways.
So the protecting group choice matters hugely.
Hugely. Lithium enolates even have a known preference order for chelation control based on the alpha substituent. It shows how even subtle structural changes can dictate the outcome. Tin-2 enolates with certain oxygen groups can also show chelation control. For boron enolates, polar effects from substituents further down the chain can enhance facial selectivity by disfavoring transition states with electron pair repulsions.
It seems like the same factors, steric, chelation, polar, are at play for the enolates phase 2.
They are indeed. And again, the choice of Lewis acid is critical in determining which pathway dominates chelated or non-chelated. Scheme 2.4 summarizes some of these enolate facial selectivity scenarios.
This level of control is amazing, but it sounds like it could get really complicated if both the aldehyde and the enolate are chiral.
It does. And that leads us to a fascinating phenomenon called double stereodifferentiation.
Double stereodifferentiation. Okay.
This occurs when both the aldehyde and the enolate are chiral. Their individual biases for specific stereochemistry, their facial selectivities don't just act independently, they interact. They can either reinforce each other or oppose each other.
Like teamwork or conflict.
Exactly. This leads to the idea of matched versus mismatched pairs. In matched combinations, the individual chiral preferences of the aldehyde and the enolate work together. They reinforce each other, leading to highly selective reactions and often a single predominant 3D isomer as the product. High diastereoselectivity.
That sounds ideal.
It is when you can achieve it. Conversely, mismatched combinations result in opposing preferences. The aldehyde wants to go one way, the enolate wants to go the other. This, as you can imagine, leads to diminished overall stereoselectivity and often a mixture of products.
So you get lower yields of the desired product or a harder separation?
Precisely. This concept of matched and mismatched pairs is a critical consideration when designing complex synthetic routes, really pushing chemists to select the perfect chiral partners to maximize the desired outcome. Scheme 2.5 shows some great examples of how these interactions play out in real reactions.
So if controlling stereochemistry is so crucial, what's a chemist to do when the starting materials aren't inherently chiral, or when you need absolute control over the handedness, the enantiomer?
That's where chiral auxiliaries come into play. Think of them as a helping hand in enantioselective aldol reactions, guiding the molecule to form predominantly one specific hand or enantiomer.
A temporary chiral guide.
Exactly. The strategy is brilliant. You temporarily attach a readily available chiral molecule, the auxiliary, to one of your reactants, usually the part that will form the enolate. This auxiliary, with its own defined chirality, then imposes a high degree of facial selectivity on the subsequent aldol reaction, acting like a stencil dictating the approach of the electrophile.
What are some common ones?
Among the most powerful and widely used chiral auxiliaries are the N-acylaloxazolidinones, often derived from readily available amino acids.
Oxazolidinones.
These compounds are fantastic because they're available in enantiomerically pure forms, both left-handed and right-handed versions. This means chemists can access either enantiomer of the desired product by simply choosing the appropriate auxiliary to start with.
Very flexible. How do they work?
Well, you acylate them, attaching your desired ketone or ester fragment. Then you form the enolate, for instance, a boron enolate using dialkylboron triflate. These auxiliaries reliably steer the enolate formation towards the Z stereoisomer. Then, the auxiliary's own substituents, often a bulky group like isopropyl or phenol, strategically block one face of the enolate, directing the aldehydes approach to the other face.
So it controls both the enolate geometry and the facial attack.
Yes, it exerts multiple levels of control, and the utility is immense because after the aldol reaction has done its job and created the new chiral centers, the auxiliary can be cleanly cleaved off, maybe by hydrolysis or reduction, leaving you with your desired chiral product. And often, the auxiliary can even be recovered and reused, making the process more economical.
That's really elegant. Are there other auxiliaries too?
Oh, yes. Titanium enolates derived from these N-acylaloxazolidinones also show excellent syn and facial selectivity. There are also related thiazolidinithione auxiliaries, sulfur analogs, which can sometimes give products with the opposite absolute configuration under certain conditions. Derivatives of natural products like ephedrine, pseudoephedrine, and even menthone have also been developed as effective chiral auxiliaries, particularly for generating E-boron enolates, which lead to anti-aldol products with good enantioselectivity. Scheme 2.6 illustrates several of these.
It seems like there's a whole arsenal of these helping hands.
There really is. It's a testament to the ingenuity of synthetic chemists.
Can you also influence the stereo control just by changing the reaction conditions, even with an auxiliary present?
Absolutely. The conditions can still play a deciding role. For instance, simply changing the Lewis acid used with an N-acylaloxazolidinone enolate, or even changing its amount, can significantly alter the stereochemistry.
How so?
Well, using TO4 might give you the expected syn isomer via a Z enolate, but switching to a bulkier Lewis acid like dithialuminum chloride might actually favor the anti-isomer.
Whoa, a complete switch. Why?
It's thought that the bulkier Lewis acid complexes more strongly or differently with the aldehyde, demanding more space and forcing a different transition state geometry, possibly even changing the effective enolate geometry or reaction pathway, overriding the auxiliary's initial preference.
Amazing. What about just using more of the Lewis acid?
That can also have surprising effects. With certain titanium enolates of oxazolidinones, using an excess of the titanium reagent can actually reverse the facial selectivity.
Reverse it.
The current thinking is that the excess Lewis acid leads to a different type of chelated transition state. It might force the oxazolidinone ring to rotate, changing which face is shielded, while still maintaining the syn diastereoselectivity that comes from the Z enolate. It's subtle, but has a huge impact.
It really underscores how fine-tuning the conditions is key.
It really does. Even with the sulfur-containing thiazolidinithione auxiliaries, the facial selectivity depends on the amount of Tysyl 4 used, or whether you add something like silver hexafluoroantimonate. This likely involves removing a chloride ion from titanium, promoting chelation with the thione sulfur, changing the ring orientation and thus the facial preference because titanium has a greater affinity for sulfur.
Incredible subtleties at play. Now, the ultimate goal in many of these reactions must be achieving enantioselective catalysis, right? Using just a tiny bit of catalyst to get the job done.
Exactly. That's the holy grail in many areas of synthesis. Catalytic enantioselective aldol additions. The goal is to use just a small amount, maybe 110 mol%, of a chiral catalyst to induce very high enantioselectivity, creating almost exclusively one specific 3D hand of the molecule, often starting with acryl precursors like enol ethers.
What kinds of catalysts work here?
There's been huge progress. One important class involves chiral oxazoborolidinones, often derived from amino acids like tryptophan. Catalyst 15 in the book is a good example.
How does it work?
These boron-based catalysts coordinate to the enol ether and the aldehyde. The chiral part of the catalyst, like the indole ring from tryptophan, then physically blocks one face of the aldehyde, forcing the enolate equivalent to attack the other face, often the reef face. Figure 2.2 suggests a pi stacking interaction might be involved in shielding the SIPFA face.
Clever shielding effect.
Very clever. Other related catalysts derived from voline can achieve almost complete enantioselectivity. There are also cyclic boronates derived from tartaric acid, like catalysts 16 and 17, that are very effective in Mukiyama-Aldol reactions, sometimes turning reactions that were unselective under simple Lewis acid catalysis into highly selective ones.
What about other metals? Copper? Titanium?
Yes. Copper bisoxylene complexes, often called QBX catalysts, like Catalyst 18, are very effective, especially with ketene acetyls or thioketine acetyls. They act as chiral Lewis acids, and the BOX ligand creates a chiral pocket that dictates facial selectivity. Figure 2.3. Titanium catalysts combined with chiral binyl ligands also show excellent enantioselectivity, though they can be sensitive to the solvent used. Zirconium binyl catalysts work well too. There are even titanium salin catalysts incorporating bimethyl chirality that are highly active.
It sounds like a whole zoo of catalysts.
It is, and it doesn't stop there. Even 10 enolate reactions can be made enantioselective by adding chiral diamines, like catalyst 21. And in a true renaissance for organic chemistry, simple molecules like the amino acid proline have reemerged as star players.
Proline again. How does it work here?
Proline can act as a purely organic catalyst, an organocatalyst for enantioselective aldol additions, particularly direct additions between ketones and aldehydes. The reaction luckily proceeds through a chiral enamine intermediate form between proline and the ketone, similar to how it works in other reactions like the Mannich reaction we'll discuss. This chiral enamine then reacts selectively with the aldehyde.
Amazing that such a simple molecule can do that.
It truly is. It opened up the whole field of asymmetric organocatalysis. Scheme 2.8 provides a nice summary of examples using these various chiral Lewis acids and organocatalysts.
Okay, we've talked a lot about building molecules in a linear fashion, or adding groups side by side. But what about building rings? That seems like a crucial capability.
Absolutely. Ring formation is central to synthesizing countless natural products and pharmaceuticals. That's where intramolecular aldol reactions come in, applying the aldol reaction within a single molecule. It's truly the art of ring closure.
How does that work?
You start with a molecule that contains two carbonyl groups, or a carbonyl in a position that can form an enolate, appropriately spaced apart. Under aldol conditions, an enolate forms at one position and then attacks the carbonyl group within the same molecule, forming a new carbon bond and closing a ring.
Creating cyclic structures.
Exactly. And when it comes to ring size, there's a fascinating kinetic versus thermodynamic preference often at play.
Oh, right, like the speed versus stability thing again.
Precisely. For forming common carbocycles, 5-membered rings are generally more thermodynamically stable, lower in energy in the end, but 6-membered rings often form thousands of times faster kinetically.
Wow, that's a huge difference.
It is. This means chemists can often choose their conditions, temperature, base strength, reaction time, to favor either the faster-forming, potentially less stable 6-membered ring, or allow equilibration to the slower-forming, more stable 5-membered ring. For simple 5- and 6-membered rings, just catalytic amounts of acid or base often suffice. But for more complex or strained ring systems, those precise directed aldol techniques, like preforming the enolate, are typically employed to ensure the desired closure happens cleanly. Scheme 2.10 shows some examples.
A particularly important and, well, classic example of an intramolecular aldol reaction is the Robinson annulation, isn't it?
Ah, yes, the Robinson annulation. Absolutely, a cornerstone reaction. It's a powerful, reliable, multi-step procedure specifically designed to construct a new 6-membered ring onto an existing ketone, creating a bicyclic system.
Annulation means building a ring onto another one, right?
Correct. It's a cornerstone reaction used in countless syntheses, particularly for building steroid skeletons or other complex natural product cores, like adding a specific new wing onto our molecular castle.
How does the sequence work?
It's elegant. It starts with a conjugate addition, a Michael addition. An enolate, usually from a ketone or a related compound, adds in a 1-4 fashion to an alpha-beta unsaturated ketone, like methylvinyl ketone, MVK, which is a very common partner.
So Michael addition first.
Yes. This creates a 155 dicarbonyl intermediate. This intermediate then undergoes an intramolecular aldol addition. The enolate from one ketone attacks the other carbonyl group, folding the molecule up to form the new 6-membered ring.
Aldol condensation closes the ring.
Exactly. This is usually followed by a dehydration step, loss of water, often under the reaction conditions, to yield a stable alpha-beta unsaturated cyclohexanone derivative. And importantly, you can apply kinetic control principles to the initial enolate formation to control which enolate forms if the starting ketone is unsymmetrical, thus controlling the regiochemistry of the annulation.
That's clever. Can it be done enantioselectively?
Yes. And this was a major breakthrough. The amino acid L-proline acting as an organocatalyst again.
Proline the superstar.
It really is. Proline can catalyze an enantioselective Robinson annulation. It forms a chiral enamine intermediate with the ketone, which then undergoes the Michael addition and subsequent cyclization sequence with high enantioselectivity, often yielding predominantly one specific 3D hand of the bicyclic product. Scheme 2.11 shows examples, including this proline catalyzed version.
Amazing. Now, beyond carbon-oxygen double bonds, we also see similar chemistry with their nitrogen analogs.
Yeah.
Enamines and iminium ions.
That's correct. Enamines, CNR, and especially iminium ions, CNR2+, are like the nitrogen versions of carbonyls. They have an electrophilic carbon atom and readily undergo similar nucleophilic additions.
How does their reactivity compare?
Generally, iminium ions with the positive charge on nitrogen are more reactive electrophiles than neutral imines. And imines, in turn, are typically a bit less reactive than the corresponding aldehydes or ketones. This often means reactions involving imines or iminium ions might require slightly different conditions, often mildly acidic, to help generate the more reactive iminium species.
What kind of products do you get?
The addition of enols or enolates to these enions or iminium ions provides a really important route to synthesizing beta-aminoketones or related compounds, which are valuable building blocks for many nitrogen-containing molecules, including alkaloids and pharmaceuticals.
And this brings us to another cornerstone reaction in this area. The Mannich reaction, often called the amino-methyl installer.
That's a great nickname for it. The Mannich reaction is essentially the condensation of an enolizable carbonyl compound, one that can form an enol or enolate with an enium ion. What it effectively does is precisely introduce an alpha-diol calaminomethyl substituent directly onto the carbonyl compound. CH2NR2 grouped next to the carbonyl.
Very useful for building up complexity. How is the iminium ion usually made?
It's often generated in situ, meaning right there in the reaction mixture, typically from a simple secondary amine like dimethylamine and formaldehyde, often under acidic conditions.
So you just mix the ketone, amine, and formaldehyde.
Often, yes, in what's called the classical Mannich reaction. It's primarily limited to secondary amines because primary amines can lead to further reactions and complications. However, there are more modern preformed iminium ion equivalents.
Like what?
Well, compounds like bis-dimethylaminoethane can generate an iminium ion with trifluoroacetic acid. Even better is N-dimethylene ammonium iodide, known as Eschenmoser salt.
Eschenmoser salt. Heard of that.
It's commercially available, quite reactive, and it's basically a stable source of the CH2 and Me2 plus desiccation. It can react directly with preformed enolates or enol ethers, allowing the Mannich reaction to proceed under much gentler, non-acidic conditions, which is a big advantage for sensitive molecules.
What's the synthetic value of the products, Mannich bases?
Oh, they have significant synthetic utility. They aren't just final products, they're valuable intermediates. You can treat these dialcalaminomethyl ketones, the Mannich bases, with base and then heat them, or quaternize the nitrogen and then eliminate it. This cleanly removes the amino group and generates an alpha-methylene carbonyl compound and a none.
Ah, forming an alkene next to the carbonyl.
Exactly. These alpha-methylene carbonyl structures are particularly important motifs as they form the reactive core of many biologically active natural products, like the anti-leukemic compound vernolipin mentioned in the text.
And you mentioned the historical significance?
Yes, the Mannich reaction has deep roots in biomimetic synthesis, trying to mimic nature's synthetic pathways. It's thought to be involved in the biosynthesis of many nitrogen-containing natural products, especially alkaloids. The classic, historically significant example is Sir Robert Robinson's synthesis of tropinone back in 1917.
1917, that's early.
It was a landmark achievement. He essentially mixed succindialdehyde, methylamine, and acetone dicarboxylic acid under physiological-like conditions and got tropinone, a complex alkaloid structure, in one pot. It was a stunning demonstration of biomimetic synthesis and the power of the Mannich reaction.
Building on that legacy, chemists have now developed enantioselective Mannich reactions, right, for precision aminomethylation.
Absolutely. Achieving enantiomer control in the Mannich reaction has been a major focus. Chiral catalysts have been key. For instance, certain chiral gold catalysts, like catalyst 22, are used effectively with silly-enol ethers and specific N-arylamines, achieving remarkably high enantiomeric purity in the beta-amino ketone products.
Gold catalysts. Interesting. What else?
Chiral zinc catalysts, like 23, have shown effectiveness for specific ketone and amine combinations, often giving high diastereoselectivity, favoring one relative arrangement, and good enantioselectivity. Copper bisoxazine, QBox catalysts, which we saw in octal reactions, are also active here for reactive amines.
Let me guess. Proline.
You guessed it. Proline makes yet another triumphant return here. It acts as a versatile organocatalyst for direct enantioselective Mannich reactions between ketones, aldehydes, and amine.
How does the selectivity work with proline here?
It often leads to specific syn selectivity between the newly formed CC and CN bonds, although isomerization to the more stable antiproduct can sometimes occur. The proposed transition state is similar to the proline-catalyzed aldol, involving that chiral and amine intermediate, but different steric effects in the Mannich transition state seem to favor the syn product.
Fascinating. Any other catalysts?
Yes. There are also other types of hydrogen bonding organocatalysts, like theoria-based catalyst 24, that work well, especially for protected enamines like enmosamines, relying on non-covalent interactions to achieve stereo control. Scheme 2.12 gives examples of these various Mannich reactions and their catalysts.
Seems like the Mannich reaction is incredibly versatile. What about even more reactive aminium-type species?
Good point. N-acylaminium ions possess even more reactive carbon-nitrogen double bonds than simple aminium ions. The acyl group attached to the nitrogen makes the carbon even more electron deficient.
Hyperreactive.
Pretty much. Their structure influences reactivity, too. Cyclic N-acylaminium ions, where the acyl group is part of the ring, endocyclic, are generally more reactive than those where it's attached externally, exocyclic. And 5-membered rings tend to be a bit more reactive than 6-membered ones, likely due to ring strain maximizing the polar effect. These are usually generated in situ from precursors like partially reduced imides or oxidized amides. They readily react with nucleophiles.
Okay, related to this, but maybe simpler, are amine-catalyzed condensation reactions like the novanagal condensation.
Right, the novanagal condensation. This reaction forms alpha-beta unsaturated compounds, often CC double bonds, and it usually proceeds via iminium ion intermediates formed transiently between the amine catalyst and one of the carbonyl components.
So the amine acts as a catalyst to form a reactive intermediate.
Exactly. It's often catalyzed by amines or amino acid buffer systems. The protonated amine, the aminium ion, is likely the key electrophilic species that gets attacked by the nucleophile.
What kind of nucleophiles work here?
A key requirement for the nucleophile is that the carbon nucleophiles must be relatively acidic compounds. They typically need 2 electron-withdrawing groups attached to the carbon that becomes the nucleophile.
Why is that necessary?
Because the amine catalysts are usually weak bases. You need that extra acidity so the amine can generate enough of the enolate nucleophile for the reaction to proceed at a reasonable rate. Common examples are malonate esters, cyanoacetate esters, or even nitroallocanes. These doubly activated methylene compounds are acidic enough.
And does anything else happen?
Yes, that high acidity also facilitates the final elimination step, usually loss of water, that forms the CSE double bond, which helps drive the reaction to completion. Also, if you start with reactants like malonic acid or cyanoacetic acid, decarboxylation, loss of CO2, often occurs after the condensation, sometimes in a concerted fragmentation.
Yeah.
Pyridine is often used as a catalyst for this decarboxylation step. Scheme 2.13 shows some examples.
Right, forming those activated double bonds. Very useful. Okay, let's shift focus again, this time to precision construction involving acylation and then olefination. First, acylation of carbon nucleophiles. You describe this as adding a carbonyl punch.
Yeah, that's a decent way to think about it. Acylation is about installing an acyl group, typically an RCO group, onto a carbon nucleophile.
How does it work generally?
It involves the carbon nucleophile adding to a carbonyl compound that has a potential leaving group attached to the carbonyl carbon. Think of things like esters, acyl halides, or anhydrides.
So COA with a group that can leave.
Right. The nucleophile adds to the carbonyl carbon, forming a tetrahedral intermediate. This intermediate then collapses, kicking out the leaving group, like an alkoxide from an ester or a halide from an acyl halide, resulting in the net acylation of the carbon nucleophile.
Got it. Additional elimination.
Exactly. A classic example is the ester condensation, or Claisen condensation.
Like, right.
Here, the enolate of one ester molecule reacts as the nucleophile, attacking the carbonyl group of a second ester molecule. The leaving group is an alkoxide ion. The product is a beta-keto ester.
Forms a new CC bond and a ketone next to the ester.
Precisely. But perhaps the more synthetically crucial variant is the intramolecular version, called the Dykman condensation.
Dykman. Okay, the ring-closing version.
Yes. It's the intramolecular Claisen. You start with a diester, and under basic conditions, one end forms an enolate and attacks the ester group at the other end, forming a cyclic beta-keto ester. It's a powerful and widely used method for forming 5- and 6-membered rings, and sometimes larger ones too.
How does control work here? Kinetic or thermodynamic?
Because the Claisen and Dykman condensations are generally reversible under the reaction conditions using base like sodium ethoxide, the product structure is ultimately governed by thermodynamic control.
Stability wins again.
Yes, the reaction favors the formation of the most stable possible product, which is often the one whose corresponding enolate is most stable because the final product usually gets deprotonated by the base. The example in the text with diester 25 is great. It yields only cyclic product 27 because the alternative closure product, 26, cannot form a stable enolate under the reaction conditions. In fact, if you make 26 separately and treat it with base, it isomerizes to 27. Scheme 2.14 shows both intermolecular Claisen and Dykman examples.
Very clear example of thermodynamic control. What about other acylating agents besides esters?
Well, acyl halides and mixed anhydrides are much more reactive acylating agents than esters. They react very effectively with less reactive enolates, like the magnesium enolate of diethylmalonate, for example. Acylimidazylides are sort of intermediate in reactivity and are also useful for acylating ester enolates or even the anion of nitromethane. N-methoxy and methylamides, also known as weinrebamides, are another valuable class of reagents for acylating ester enolates without overaddition.
Weinrebamides, right. And can you acylate silyl ethers?
Yes, silyl ethers react well with acyl halides in the presence of Lewis acids, like SNCl4 or TiClO4. This is a good way to make beta-diketones. Scheme 2.15 has examples of these acylations.
Can you acylate ketones directly using esters?
You can. This pathway also yields beta-dicarbonyl compounds, which are often quite acidic and can be easily alkylated further if needed.
What kind of esters work?
A common reaction uses formate esters, like ethyl formate, reacting with ketone enolates. This gives beta-ketoaldehydes, although these often exist predominantly in their enol form, sometimes called hydroxymethylene derivatives. Again, product formation here is usually under thermodynamic control.
Any other examples?
Sure. Ketones can be converted to beta-keto esters using diethyl carbonate or diethyl oxalate as the acylating agent. Alkyl cyanoformates can also be used, sometimes under kinetic enolate conditions. It's interesting, if you quench these reactions with trimethylsilate chloride instead of acid, you can sometimes isolate a stable silly ether of the tetrahedral intermediate, showing it can have some stability before collapse.
That's neat. What about beta-keto sulfoxides?
Yes. Those are formed by acylating the anion of dimethyl sulfoxide, DMSO anion, dimsilanion, with esters. They are very useful synthetic intermediates.
How so?
The sulfoxide group can be reductively removed using something like aluminum amalgam, which yields a methyl ketone. Or you can alkylate the beta-keto sulfoxide first at the carbon between the carbonyl and sulfoxide, and then reduce, which allows you to build up longer carbon chains effectively. Scheme 2.16 shows examples of these ketone acylations and the sulfoxide chemistry.
Lots of ways to add that carbonyl punch. Now let's move to olefination reactions, making C double bonds, right?
Exactly. Olefination reactions are all about forming carbon double bonds or olefins with purpose.
And the key challenge, as always it seems, is controlling the stereoselectivity, getting EVSE.
That's often the crucial aspect, yes. Making sure you selectively form either the E-alkene, which usually corresponds to transgeometry, or the Z-alkene cis geometry.
And the undisputed phosphorus powerhouse in this field is the Wittig reaction.
Absolutely. The Wittig reaction is a giant in organic synthesis. It involves these fascinating reagents called phosphonium ylides.
Ylides again. The ones with adjacent charges.
That's them. They are often represented by resonance structures, one with opposite charges on adjacent carbon and phosphorus atoms, the Da12 form, pH3P plus tau-Ara2, and one with a double bond, the Ylene form, pH3PCr2. The dipolar ylide structure is generally considered the dominant contributor. These ylides are highly reactive nucleophiles.
How does the reaction work?
Phosphonium ylides react with carbonyl compounds, aldehydes, or ketones to famously produce olefins in triphenylphosphine oxide, PH3PO, as a byproduct. The driving force is the formation of the very strong phosphorus-oxygen double bond.
What's the mechanism?
It's generally accepted to proceed through an initial cycloaddition to form a four-membered ring intermediate called an oxyphosphatane. Before that, there might be a transient butane intermediate with separated charges, especially under certain conditions. This oxyphosphatane then fragments, breaking the CP and CO bonds and forming the CC and PO bonds.
How are the ylides made?
Typically, you make a phosphonium salt first, usually by reacting triphenylphosphine with an alkyl halide via an SN2 displacement. Then you deprotonate this phosphonium salt using a strong base, like organolithium reagents, N-dually, or strong amines bases like sodium amide or NaNH-MDS to generate the reactive alide.
How reactive are they?
Non-polar ylides, those where the carbon bears alkyl or aryl groups, are highly reactive and react readily with both ketones and aldehydes. Ylides that are stabilized by an electron withdrawing group attached to the halidic carbon, like an ester ketone group, are less reactive, often only reacting well with aldehydes.
And the stereoselectivity. How do you control E vs Z?
That's a huge topic in Wittig chemistry. For non-stabilized allies reacting with aldehydes, the conditions matter a lot. Using strong bases that don't involve lithium, like sodium amide or sodium hexamethyl disalyzide, NaHMDS, often gives higher selectivity for the Z-alkene cis. This is often referred to as the salt-free condition.
Why does lithium affect it?
Using alkylithium reagents as the base often diminishes the Z selectivity, possibly due to the lithium cation coordinating in the transition state or forming complexes with the butane intermediate, making the reaction pathway less stereoselective or favoring the E-alkene under reversible conditions.
So salt-free often means Z-selective. What if you want the E-alkene?
That's where the brilliant Schlosser modification comes in, specifically for non-stabilized ylides reacting with aldehydes. It's an ingenious procedure to achieve high E-alkene trans stereoselectivity.
How does it work? It sounds complex.
It is a multi-step, one-pot sequence. First, you form the lylide and react it with the aldehyde at low temperature, forming a mixture of intermediate butane-lithium halide complexes. Then you add another equivalent of strong base, like phenolithium, at low temperature. This deprotonates the carbon alpha to the phosphorus, forming a beta-oxidoylide. This intermediate equilibrates to the more stable stereoisomer. Then you carefully add a proton source, like T-butyl alcohol, which stereoselectively protonates the beta-oxidoylide to give predominantly the syn-butane-lithium halide complex. Finally, warming this complex induces a syn elimination, different from the usual Wittig elimination, to give selectively the trans-alkene.
Wow, that's quite a sequence, but it delivers the E-alkene.
It does, often with very high selectivity. It's a powerful tool when you deal with the trans isomer. Then the Wittig isn't just for simple alkyl groups. You can use functionalized ylides too, right?
Absolutely. You can use methoxymethylene or phenoxymethylene ylides, which react to give vinyl ethers. These vinyl ethers can then be easily hydrolyzed with acid to yield aldehydes, effectively adding a one-carbon aldehyde unit. Alkyl thiosubstituted ylides give vinyl sulfides, which also have synthetic uses. Scheme 2.17 shows various Wittig examples.
Okay, so the Wittig is powerful, but sometimes gives mixtures or involves complex modifications. What are the alternatives? You mentioned phosphonate anions.
Right. That leads us to the Horner-Wadsworth-Emmons reaction, or HWE reaction. It's an extremely important complement, sometimes even preferred over the Wittig. It uses phosphonate carbanions instead of phosphonium ylides.
How are they different?
Phosphonate carbanions are generated by treating alkyl phosphonate esters, typically diethyl or dimethyl phosphonates, POR, to CH2R with bases. These bases can range from strong ones like sodium hydride or N-butyllithium to milder ones like sodium dithoxide, or even solid bases like potassium fluoride on alumina. These anions are generally more nucleophilic than stabilized Wittig ylides and react readily with aldehydes and ketones.
What's the advantage?
One major advantage is that the byproduct, a phosphate ester, is water-soluble, making purification much easier than removing triphenylphosphine oxide from the Wittig. Also, HWE reactions involving stabilized phosphonate anions, like those with an adjacent ester group, often show excellent stereoselectivity for the E-alkene trans. So HWE often gives E alkenes reliably. What if you need the Z alkene from an HWE type reaction?
That's traditionally harder, but there are specific methods. The Stilgen-Array modification is a key example. It uses phosphonate esters with electron-withdrawing groups, like trifluoroethyl, and specific bases, like KHMDS with 18-crown-6 ether and THF at low temperature. These conditions strongly favor the formation of the Z-alkene, particularly for making alpha-beta unsaturated esters and amides.
Still Gennari for Z alkanes. Got it.
Right. And other modified phosphanoacetate esters, like phenyl or specific fluorinated phenyl esters, have also been developed to give good Z selectivity with aldehydes. Even specific conditions, like using potassium carbonate with crown ether or adding excess sodium iodide, can push the selectivity towards Z. There's also a useful variant using lithium chloride and an amine base, like DBU or DIP, which works well for large-scale synthesis.
What about phosphine oxides?
That's the Horner-Wittig reaction, distinct from HWE. Carbanions derived from phosphine oxides also add to carbonyl compounds. The initial adducts are usually stable beta-hydroxy phosphine oxides. These can often be separated into diastereomers. Then, heating these adducts with a base like sodium hydride causes elimination to form the altamine. Crucially, since you can often separate the intermediate diastereomers, you can control the alkene geometry by choosing which diastereomer to eliminate, as the elimination is stereospecific, often anti. Scheme 2.18 shows HWE examples.
Okay, another olefination strategy involves silicon, the Peterson reaction.
Yes, the Peterson olefination. It leverages the fact that trialkylsyl groups, like trimethylsily, TMS, can stabilize an adjacent carbanion, alphasyl carbanion.
How does it work?
These alpha-lithiosilanes react with aldehydes or ketones to form beta-hydroxylcosilanes as intermediates. These intermediates are then converted to alkenes by elimination, induced by either acid or base.
Acid or base, doesn't matter which.
Critically, yes. The stereochemical outcome of the elimination is different. Acidic conditions typically promote an anti-elimination pathway, while basic conditions, like using KH and THF, promote a syn-elimination pathway, often via a cyclic intermediate involving silicon and oxygen.
Anti with acid, syn with base. So you can choose the conditions to get the E or Z alkene if you can control or separate the intermediate diastereomers.
Exactly. That's the power of the Peterson. In some cases, especially with substituted alpha-lithiosilanes, the intermediate fragments spontaneously under the reaction conditions to give the alkene directly. While may be less widely used overall than Wittig or HWE, Peterson is advantageous for preparing certain types of olefins, especially those that might be unstable and can sometimes be more reactive than stabilized Wittig halides. Scheme 2.19 has examples.
And the last major olefination we should cover is the Julia reaction, the cell phone solution.
Right, the Julia olefination and its variations. The core idea involves the addition of a sulfonyl-stabilized carbanion, an alpha-sulfonyl carbanion, to an aldehyde or ketone. This forms a beta-hydroxy sulfone adduct. The subsequent steps then eliminate the sulfone group to form the alkene.
How does the elimination work?
The original version, now often called the Julia-Lithgow olefination, involved first acylating the hydroxyl group of the adduct, making an acetate or benzoate ester, and then treating it with a reducing agent like sodium amalgam, AHG, or samarium diodide, SMI2. This reductive elimination typically favors the formation of the E-alkene tran.
Reduction needed. That sounds a bit harsh sometimes.
It can be. That's why the development of the modified Julia, often called the Julia-Kosienski olefination, was a major advance. This version uses specific heteroaromatic sulfones, most commonly benzothiazole, BT sulfones, or tetrazote sulfones.
Why those specific sulfones?
Because the adducts formed from these sulfones can undergo elimination under non-reductive conditions, usually just treatment with a base like KHMDS or NaHMDS. The elimination mechanism is different, likely an addition elimination sequence involving the heteroaromatic ring that ultimately fragments to the alkene, nitrogen gas for tetrazoles, and a salt byproduct. It avoids the often harsh reductive conditions of the original Julia-Lithgow, making it much more versatile and popular in modic synthesis. Scheme 2.20 shows examples of both types.
Julia-Kosienski sounds like a very practical improvement.
It really was. Huge impact.
Okay, let's venture into reactions that proceed by addition followed by cyclization, particularly for making three-membered rings like epoxides and cyclopropanes.
Right. This is a unique pathway where the carbon nucleophile itself contains a built-in potential leaving group. After the initial nucleophilic addition to a carbonyl group, the newly formed oxygen anion, the alkoxide, attacks internally, displacing that leaving group on the original nucleophile and forming a new ring.
Intramolecular attack closes the ring.
Precisely. One prominent group of reagents that react this way are the sulfur halides. They are the true epoxide and cyclopropane makers of this category.
Sulfur halides again. We mentioned them as nucleophiles earlier. How do they form rings?
Common examples are dimethylsulfonium methylide, Me2S plus NeCH2, and dimethylsulfoxonium methylide, Me2S plus NeCH2, often called Corey's halides. They are prepared by deprotonating the corresponding sulfonium or sulfoxonium salts with a strong base.
How are they different from the Wittig halides?
Crucially, unlike phosphonium halides, which give alkenes, these sulfur halides react with aldehydes and ketones to yield epoxides.
Epoxides, not olefins. Why?
Because the intermediate adducts formed after the halide attacks, the carbonyl undergo a rapid intramolecular SN2 displacement. The newly formed alkoxide oxygen attacks the carbon bearing the sulfur group, and the sulfur moiety, Me2S or Me2SO, acts as the leaving group.
Ah, the oxygen kicks out the sulfur.
Exactly. The sulfur acts as both the anion stabilizing group to form the halide and the leaving group in the subsequent cyclization. It's very efficient.
Do the two different halides behave the same way, the sulfonium versus sulfoxonium?
No, and this is fascinating. They show distinct selectivity. Dimethylsulfonium methylide, the one without the oxygen on sulfur, is generally more reactive but less stable. With alpha-beta unsaturated carbonyl compounds, it typically reacts via direct 1-girl-2 addition to the carbonyl, followed by rapid cyclization to form the epoxide attached to the double bond. The intramolecular displacement is faster than any potential reversal of the initial addition.
So the sulfonium halide gives epoxides even with enones.
Usually, yes. In contrast, dimethylsulfoxonium methylide with the S-azo bond is more stable but less reactive. With alpha-beta unsaturated carbonyls, it often reacts via conjugate addition, 1/4 addition first. The resulting enolate then undergoes intramolecular displacement of the sulfoxonium group to form a cyclopropane ring fused to the carbonyl system.
Whoa, so sulfonium gives epoxides, sulfoxonium gives cyclopropanes with enones.
That's the general trend, yes. It's thought that for the sulfoxonium halide, the initial 1-vol-2 addition might be more reversible, allowing a thermodynamically favored conjugate addition pathway to take over, leading ultimately to the cyclopropane. Their differing selectivities with simple cyclohexanones, axial versus equatorial attack preferences, also highlight their distinct reactivity profiles, likely related to stability and reversibility.
That's a really useful distinction. Can they transfer other groups besides CH2?
Yes, related sulfur manolates can transfer substituted methylene units like isopropylidene, making gem-dimethyl epoxides, or even cyclopropylidene groups. The oxbaropentanes, formed with cyclopropyluteolates, are valuable intermediates that can rearrange under thermal or acidic conditions to form cyclobutanones. There are also related chiral sulfoxamines that can act as chiral alkylidene transfer reagents. Scheme 2.21 shows examples, including the cyclopropanation.
Another classic reaction involving addition cyclization is the Darzens reaction, right? For making epoxy esters.
Yes, the Darzens reaction, sometimes called the Darzens glycidic ester condensation, it's an older but still very relevant technique.
How does that one work?
The enolate of an alpha haloester, like ethyl chloroacetate, adds to an aldehyde or ketone. The resulting alkoxide oxygen then performs an internal SN2 attack, displacing the halide, chloride or bromide, on the adjacent carbon and forming an alpha-beta epoxy ester, also called a glycidic ester.
So enolate attacks carbonyl, oxygen kicks out halide, makes an epoxide ring next to the ester.
Exactly. It's a reliable way to make these specific structures. There's also a silicon variant where an alpha-chlorolithium reagent derived from chloromethyltrimethylsilane reacts with aldehydes or ketones to give trimethylsilane epoxides. Scheme 2.22 shows Darzens examples.
Okay, let's circle back now to conjugate addition by carbon nucleophiles, the Michael reaction. We touched on it earlier.
Right, the one-off alipha attack. Just to reiterate the core concept, it's the addition of a nucleophile to an electrophilic multiple bond, typically a carbon double or triple bond that's activated by an electron withdrawing group, EWG, like a carbonyl, nitro, cyano, or sulfonyl group. This is distinct from direct 1-gal-2 addition to a carbonyl carbon.
And the product structure is characteristic, right? A 134 relationship between the nucleophile and the activating group.
Exactly. Conjugate addition typically forms a bond alpha to one EWG, the one that was on the nucleophile, and beta to another EWG, the one activating the multiple bond, leading to a 1,4,5 or sometimes 1,0,5 decarbonyl or related functionalized system after workup.
And you mentioned Lewis acids expand the scope.
tremendously. Lewis acids, used often in conjunction with enolate equivalents like silyarnol ethers and silyketone acetyls, similar to the Mukayama aldol, greatly expand the scope of acceptors and nucleophiles that can be used in conjugate addition. The Lewis acid can activate the acceptor or stabilize the intermediate adduct.
We also talked about the 102 versus 184 addition competition.
Yes, it often comes down to hard versus soft nucleophiles and reversibility. Highly reactive, hard nucleophiles, like Grignard reagents or simple organolithiums, tend to favor irreversible 1-girl-2 addition directly to the carbonyl.
They just hit the most positive spot fast.
Pretty much. But for less basic, softer nucleophiles, like enolates from beta-decarbonyl compounds or malanates, the 1-sphere addition is often more easily reversible. This allows the system to funnel towards the generally more thermodynamically stable 1-girl-4 addition product, which is usually irreversible under the conditions used.
So softer nucleophiles often favor 1-girl-4 addition.
That's a common generalization. When you use just a catalytic amount of base, enolates from relatively acidic compounds, like beta-keto esters, malanate esters, are highly effective myconucleophiles. And as mentioned before, fluoride ion can be a surprisingly effective catalyst for these reactions too. Scheme 2.23 shows some general examples.
Can you use preformed enolates like lithium enolates in myco reactions?
Yes, absolutely. Preformed lithium enolates can undergo conjugate addition, especially under carefully controlled conditions. Their regioselectivity, 1-metal-2 versus 1-metal-4, and stereoselectivity can be influenced by factors like the counterions, solvent, additives like HMPA, and temperature.
Is there stereo control like Sinanti?
Sometimes, yes. Similar to aldol reactions, there's evidence suggesting that Z-enolates can yield syn adducts and E-enolates can give anti-adducts in conjugate additions, possibly proceeding through some kind of cyclic transition state, although it's perhaps less well-defined than in aldol reactions.
What are good Michael acceptors besides enones?
Nitroleganes are excellent Michael acceptors.
RCH-CHNO2, why are they so good?
The nitro group is very strongly electron withdrawing, making the double bond highly electrophilic. Plus, there's no competing nucleophilic attack on the nitro group itself, unlike potential 1-Virga-2 addition to a carbonyl. So addition is cleanly directed to the beta carbon.
And the product is useful.
Very. The nitro group in the adduct can be transformed into other functional groups. For instance, it can be hydrolyzed via the Neff reaction to a ketone or aldehyde, providing a convenient pathway to 1,4,4 dicarbonyl compounds. Or it can be reduced to an enamine.
What about nitryl anions?
Carbanions derived from nitriles, alpha-cyanocarbanions, can also act as myconucleophiles. The reaction pathway can sometimes be complex, occasionally proceeding via an initial 1-Virl-2 adduct that then isomerizes to the more stable 1-Virl-4 adduct.
And the really big players for adding simple alkyl or aryl groups via conjugate addition are the organocopper reagents, right?
Absolutely essential. Organocopper reagents, like lithium dialkyl cuprates, Gilman reagents, have an extremely strong preference for 1-Val-4 conjugate addition over 1-Val-2 addition. Crucially, they do not require additional anion stabilizing substituents on the carbon nucleophile. This means you can add simple alkyl, alkenyl, and aryl groups via conjugate addition using cuprates, which is extremely difficult or impossible with most other organometallic reagents. They are covered in detail in Chapter 8, but absolutely vital for Michael-type chemistry. Scheme 2.24 shows some conjugate additions under aprotic conditions.
You also mentioned this powerful idea of conjugate addition followed by a tandem alkylation, building two bonds at once.
Yes, this is a really elegant and efficient strategy. When you perform a conjugate addition under aprotic conditions, often using stoichiometric base to preform the enolate, or using reagents like Silicon ethers with Lewis acids, the initial adduct that forms is itself an enolate, or can be trapped as one.
So the product of the first reaction is ready for a second one.
Exactly. This trapped intermediate enolate can then be directly reacted in the same pot with an electrophile, typically an alkyl halide or sulfonate, to effect a second CC bond-forming step, an alkylation. So you form the conjugate addition bond and then an alkylation bond sequentially, creating two new bonds and often multiple stereocenters with high control.
That sounds incredibly powerful.
It is. Silyketone acetyls are key players here, often undergoing conjugate addition catalyzed by Lewis acids like magnesium or lithium perchlorate. And as you might expect, chemists have developed chiral Lewis acids like those QB-ox catalysts again, or binyl derivatives of boron or titanium to achieve highly enantioselective tandem conjugate addition alkylation reactions. You can even use additives like hexafluoroisopropanol, HEPA, to accelerate these catalytic reactions.
What about other enolate types in these tandem reactions?
Stanyl enolates, tin enolates, also give good yields in conjugate additions, sometimes catalyzed by just a small amount of tetrabutyl ammonium bromide, TBAB. And nitroalkenes react well with silyonyl ethers induced by TCl4 or SNCl4, where the initial adduct can be trapped and then hydrolyzed to give gamma-keto-carbonyl compounds. Scheme 2.25 shows examples of these tandem processes.
And controlling facial selectivity in these conjugate additions is similar principles to the aldol reaction, chiral auxiliaries and catalyst.
Very much so. The same strategies apply. Chiral auxiliaries, like those N-acyloxazolidinones, can be converted to nucleophilic species, Z-titanium enolates, that achieve high diastereoselectivity in conjugate additions.
And chiral catalysts.
Yes, chiral catalysts are widely used. Those copper bisoxazoline catalysts are effective for enantioselective conjugate additions, including reactions using alpha-beta unsaturated N-siloxyzolidinones as the acceptor, achieving high enantiomeric excess. Chiral boron catalysts with bienol ligands work too. And yes, proline can catalyze enantioselective Michael additions, for instance, of beta-decarbonyl compounds to nitroalquenes. Other organocatalysts like chiral bisoxazolidines or enamines derived from chiral pyrrolidines also show high stereoselectivity in specific Michael reactions, sometimes used in the synthesis of important drugs like the antidepressant roloprane.
It seems the toolkit for controlling stereochemistry in conjugate additions is just as rich as for aldol reactions.
It really is. A lot of the core principles translate very well.
What about conjugate addition of simple organometallic reagents, like organolithiums? You said they prefer 1-2 addition. Are there exceptions?
Yes, while organolithium compounds typically prefer 1-2 addition, 1-4 conjugate addition can occur under specific circumstances.
Like when?
One key exception is with salts of alpha-beta unsaturated acids. The carboxylate anion, COO, is much less electrophilic than a ketone or aldehyde carbonyl, so 1-2 addition is suppressed, allowing 1-4 addition of alkyl or irolithiums to occur. Similarly, alpha-beta unsaturated amides can be good acceptors for 1-4 addition because the amide carbonyl is also less reactive towards 1-2 addition. These amide adducts can even be trapped as enolates and alkylated further.
Interesting niches.
Any others? Lithiated N-allyl carbamates, when complex with the chiral diamine spartine, add to nitrile alkenes with both high diastereoselectivity and high enantioselectivity. The spartine effectively makes the organolithium reagent chiral, and organozinc reagents like dialkyl zincs can undergo enantioselective conjugate addition to nitroalkenes when catalyzed by a chiral titanium tadalate complex. So there are specific methods even for simpler organometallics.
Lastly, what about cyanide ion as a nucleophile in conjugate additions?
Cyanide ion, CN, can definitely act as a carbon nucleophile in conjugate additions. Because HCN is a relatively weak acid, pKa around 9.3, the reaction is feasible even in hydroxylic solvents like ethanol, using simple salts like KCN or NaCN.
Are there better reagents?
Yes. Lewis acidic reagents like triethylaluminum hydrogen cyanide complex or diethylaluminum cyanide, ED2ALLCN, are often more effective and controlled. They likely work by coordinating to the carbonyl oxygen of the acceptor, activating it towards 1-phenyl-A addition. While ATLCN can mediate conjugate addition to substrates bearing chiral auxiliaries, achieving high enantioselectivity this way is often challenging, perhaps due to the very small size of the cyanide nucleophile, making it difficult for the auxiliary to exert strong facial control.
So we've navigated a really vast landscape today, haven't we? From the fundamental principles of carbon nucleophile addition to carbonyls and activated alkenes.
Right, the basic nucleophile-electrophile interactions.
To the incredibly intricate controls over regiochemistry, stereochemistry, and even enantioselectivity. We've explored the workhorse aldol reactions and their many variations using lithium, boron, titanium.
And the clever Mukayama-Silly enol ether approach.
Exactly. Then the critical aspects of stereocontrol, Falcon-Ann, chelation, double stereodifferentiation, and the power of chiral auxiliaries and catalysts.
Mastering that 3D structure.
Then we moved into powerful ring-building strategies like intramolecular aldol and the classic Robinson annulation.
Building cyclic frameworks.
And the vital nitrogen-containing counterparts like the Manic reaction, again with enantioselective versions. Then the diverse world of ulcimations, making double bonds precisely with Wittig, HWE, Peterson, Julia.
A whole toolkit for COC formation.
We wrapped up with those unique addition cyclization pathways, making epoxides and cyclopropanes using sulfur halides and the Darzanes reaction, and finally came full circle to the versatile conjugate additions, including tandem sequences and enantioselective catalysis.
It really covers the core methods for CC bond formation involving carbonyls and related species.
These reactions, whether they're decades-old classics or cutting-edge catalytic methods, truly are the bedrock of constructing complex organic molecules. They allow chemists to perform a kind of molecular origami with just incredible precision.
And as we reflect on the precision and versatility achieved in these reactions, often through really quite subtle changes in reagents, solvents, or reaction conditions, it's remarkable how they seem to mimic, in a way, the exquisite control seen in biological systems in enzyme catalysis.
That's a great point. It feels like we're learning nature's language.
Maybe. This constant push for exact molecular construction in the lab hints at the deep fundamental connections between synthetic organic chemistry and nature's own molecular machinery. It really makes you wonder, what further layers of complexity and control await discovery in these already classic reactions? And what might that tell us about the elegance and efficiency of life itself?
A truly provocative thought to end on. Thank you so much for joining us on this deep dive into the fascinating world of carbon bond formation through the lens of Carey and Sundberg's Chapter 2. We hope you, our listeners, feel a little more well-informed and perhaps, like us, a lot more amazed by the hidden, intricate dances happening at the molecular level all around us all the time.